So 3.5, solving logarithmic equations. And again, if you look at all of these down below, every single one of them says solve. So again, I don't want to confuse you with what you did yesterday as far as making sure that what rules do I use for what. Okay, this is very straightforward. Solve means I'm looking for x. I mean, that's the whole issue that we've been dealing with since pre-algebra or even preschool. If I give you one apple and I give Sally another apple, how many apples do you have together? We're solving equations, and we're still doing that. We're just having, our equations are looking a little trickier and more complex, but yet our toolbox in which we know how to solve things is becoming more and more full every year on different strategies in which to solve all of those equations, okay? So this is just one more method in which we can solve an equation, and therefore then we have more tools in our toolbox in which to solve it. We have a couple new properties that I want you to look at, and this is kind of a duh, but yet when given in variable form, sometimes it doesn't make as much sense. If we have two bases of an exponent that are equal to each other, we can ignore the bases and just realize then that the exponents themselves would also be equal to each other. In other words, what that's saying is that if I have x to the y equal x to the z, y is going to equal z. If x squared is equal to x raised to something, what does that something have to be? A 2. And that's why I'm saying it makes sense when it's actual numbers, but when we have variables, it's not quite so in your face, okay? And so we're going to be utilizing this in exponential form. If my base is the same, therefore then my exponents have to be the same. Okay, so that's this first rule. The second one, if my log bases are the same, then u and v have to be the same. So for instance, if I have log base 2 of 3, but I know log base 2 of x, what does x have to be? X has to be 3. If the log base is the same, then my u and my v also have to be the same. Okay, so we're going to be applying those principles as we move forward. Before we get started, I want you to number all 8 of these problems, and I'm going to number them across 1, 2, 3, 4, 5, 6, 7, and 8. We are not going to be working these in order, because if I do, I might have a couple of you just shut down and be done, okay? So we're going to start with those that I consider to be some of the easier ones, and then working up to more complex, all right? So that means that we're going to start with number 3. We're going to start with number 3. The purpose of a logarithm, one of the purposes of logarithms, is to be able to solve a variable in exponential form. And so we want to, when the directions say to solve, you know that you can go from logarithmic form into exponential form to solve, and then vice versa. If it's in logarithmic form, then I can go into exponential form. True story. Husband and I out to eat Friday, Saturday night, not sure which night, and I run into a former classmate, a former student. Okay, she's a former student. And she's like, oh my gosh, Mrs. Myron, she's at John Wood as we speak, and she's taking a class online, the Alex math class. And she said that she was working with logarithms. And she said, believe it or not, Snail, boom, came to mind. She knew exactly how to solve it. And she goes and she got it right, all because of that silly, stupid method, the Snail method. Okay, as stupid and silly as it may seem, it's something that you'll remember. It's something that you'll remember. So with that being said, with that being said, we will be utilizing that. So we have Meyer's method of logistic functions right there. Thank you, Madeline. Look at that beautiful snail, okay? So we have that. Now, look at number 3. We're going to start with number 3. The first question I'm going to ask you is do I have any logs? Do I have a logarithm? Yes. How many logs do I have? Just one. That's critical. If I have just one logarithm set equal to something, and I'm looking for either the base, or if I'm looking for this, then I am going to rewrite it into exponential form in order to solve. And rewriting into exponential form is nothing more, guys, than using the snail method. What's the base here if it's not written? 10. Once a base, always a base, start with the base. So I'm starting with the base, and I'm going to snail around, and the snail tells me the order in which I'm writing my numbers. That's all it does in exponential form. It just gives me the order in which I write my numbers. So my base is 10, raised to the 3.724, and that's going to give me x. That's it. Type in your calculator, 10 raised to the 3.724. And since this is out to the thousandths place, then your answer also should be representing that many, or that number of decimals as well. So 5,296 and 634 thousandths would be my answer. Therein lies when and how we use that snail method. Start with the base, we snail around, and again, that method tells us the order in which we write the numbers, which place that goes into. So 10 raised to the 3.724 is equal to x. And then I just type that strictly into my calculator. Okay, questions on that? All right, move over to number 4. I'm in logarithmic form. How do I know that? There's my log right there. Any suggestions on how I can start this? Yeah, I can snail it again. Once a base, always a base. Start with the base. So I snail it around. So I get 10 squared equals x squared. What do I do to both sides to get rid of the square? Square root. And what is 10 squared before I kind of jumped ahead? Take the square root of both sides. So x equals 10. What about that 10 though? It's a plus or minus 10 because it's squared. Okay, so fairly straightforward on both of those. We have one logarithm in perfect form to where I can snail it around. Done. And just solve it appropriately. So questions on 3 and 4. We use the same method for both of those. All right, so let's look at number 5. Do I have, am I in logarithmic form? Yes, but how many logs do I have on number 5? 2. But here's the next question. Are they the same base? Yes, they both have the same base. Log base what? 10. If they both have the same base, it's kind of like if I multiply both sides of an equation by 2, I can just cancel 2 out because if it's happening to both, they just both cancel out. Same principle. I can just cancel my logs out if it's the same base. And if there's one log equal to a second log, if it's just separated by an equal sign, I'm good to go. So therefore then, I have 4x minus 3 is equal to 5. And now I have an algebra problem. So take it from there and solve for x. So 4x go to 8, x equals 2. Okay? That's a key key component in solving is recognizing that I have the same base of a logarithm, or it could be natural log on either side. But the problem is, or no, not the problem is, but the simplicity of it is, both of those logs are separated only by an equal sign. Because when you look at number 6, I'm in logarithmic form. But how many logs do I have? 3. I have 3. I can't be quite as simple as I was on number 5. If 2 logs are being added together, and so this is yesterday. This is the practice sheet that we had yesterday. I want to simplify this. I want to condense this down to 1 natural log. How do I rewrite this? Natural log. This is what you guys did yesterday. If it's being added together, what's going to happen to these two? I'm going to multiply them. So I have 3x minus 2 times x minus 1 equal to, and if this 2 is out in front, where does that actually belong? Natural log of x squared. Okay? This is just stuff you did yesterday on that worksheet. What now do I notice? I'm down now to 2 natural logs. And since it's a natural log, it automatically has the same base. So the same thing as I did with my logarithms above, natural logs cancel out. And I'm left with a quadratic equation. So now we go back to algebra 2, where I have 2 binomials being multiplied together. I can use FOIL, so I get 3x squared minus 3x minus 2x plus 2 equals to x squared. I can simplify my like terms. So I get 2x squared minus 5x plus 2 equals to 0. Anytime I've got a quadratic, we want to set it equal to 0. I can either factor it, and in this case, that looks like what I will be doing. So a times c gives me 4. This x squared, to get it equal to 0, I bring the x squared over. Subtract x squared from both sides. So multiply to give me positive 4, but add to be negative 5. Negative 4 and negative 1. So the negative 4 and the negative 1 is going to split my negative 5x into 2x squared minus 4x minus 1x plus 2 equal to 0. I go into grouping. I can pull out a common factor of 2x. I get x minus 2, pull out a common factor of negative 1, and get x minus 2. So x minus 2 is my common factor again, with 2x minus 1. So each one of those equal to 0. So x will be 2 and x will be 1/2. So we want to always make sure that after we solve for an equation, we want to make sure that our restrictions are still being respected. Okay, so we don't ever want anything to still end up as 0 in the denominator with one of our answers or solutions. We want to make sure that we still don't have a negative under the radical if we're looking for only real numbers. And in this case, we want to make sure that whatever inside those parentheses can't be negative. Okay, we cannot have a negative inside those parentheses. So therefore, I'm going to double check. I'm going to take 2. What's 3 times 2? 6 minus 2? Positive number. I'm good to go. 2 minus 1, 1, good to go. Now I'm going to take 1/2 times 3. I get 3/2, which is the same thing as 1/2. What's 1/2 minus 2? Positive or negative? 3/2 minus 2 is a negative. Okay, so that's a negative and that's a negative as well. So therefore, x minus 2 really is not a solution, just my positive 2. Okay? Can't have negative inside parentheses. Okay, guys, 3, 4, 5, and 6. We've done all 4 of those. Questions on those? Okay, moving on. Number 7. Number 7. Again, we're solving equations. Where's the variable here located? In the exponent. So am I in logarithmic form or exponential form? I'm in exponential form. So probably, since I'm in exponential form and the variable is in the exponent position, I'm probably going to go and convert into logarithmic form before it's all said and done. Okay? But before I do that, I need to isolate my base and the exponent. I need to isolate that. So what would be my first step? Divide by, perfect. I'm going to divide both sides by 80. So I'm left with e raised to the 0.045x. 240 divided by 80 is 3. Now the only time that you can do Snail is if the logarithmic form is given, okay? Well, or I'm trying to move into exponential form, okay? But here, and I'm in this situation in which I can go ahead and solve. Here, it wouldn't help me at all, okay? So therefore, if I've got a base e, and I want to get it into logarithmic form, I've got a base e and I want to get it into logarithmic form, what can I bring in to both sides of the equation, because what I do to one, I must do to the other, in order to help simplify this? This is my key right here. If I want to go from exponential to logarithmic form, I'm going to bring in ln. Okay? If I bring it into the left side, I then also have to bring it into the right. So natural log e to the 0.045x equals natural log 3. And notice I just threw it in there. One on the left, one on the right. I was not in logarithmic form, I was in exponential form. So I'm trying to convert it to logarithmic form, and I can do that by bringing the natural logs in on both sides. What happens to the left? They cross out, because what's my base down here? That crosses out, so I'm left with 0.045x equals, well, grab your calculator and tell me what's the natural log of 3. 99? Yeah. Does that sound good? Yeah. Okay, solve for x. And since that's positive, that would keep that as positive, so we're all good. I'm in exponential form. I want to rewrite it into logarithmic form so that I can solve. I can do that by bringing in natural log on both sides. The natural log e and base e cancel out, and I'm left with just the exponent of 0.045x, and then natural log 3 on my calculator is 1.099. Divide both sides by 0.045, and I get x is 24.41. Okay, questions? Now we're just kind of traipsing right through. Okay, let's look at number 8. Solve. I see no word, I see no logarithm, I see no natural log, so I can assume that I'm in exponential form. And here's my base and my exponent, so I know that I need to get that all by itself before I can convert over to natural log. So what would be my first step? I need to subtract 7 because I need to get this by itself first. So I'm going to subtract 7 from both sides. So I get negative 3 e to the opposite of x equals negative 5. What do I do to both sides? Divide by negative 3. So I have e to the negative x equals 5/3. Now that e is isolated, now what can I bring into both sides? You knew we were getting there. And now this is work just like what the other one is. The natural log and the e cancel. So I'm left with the opposite of x equals, and what's the natural log of 5/3? Divide both sides by negative 1, so x equals negative 0.5108. So really, 7 and 8 worked fairly similar. I'm in exponential form, needed to get it to logarithmic form. 3, 4, 5, and 6 might have looked like it was drastically different, but all of them were in logarithmic form. We eventually got it into exponential form. Some took a little bit longer to get to than others, but that was the premise, is going from logarithmic to exponential, exponential back to logarithmic form. Okay? So let's go now to number 1.
Is Pam in class?
40 times 1/2 raised to the x over 2 equals 5. Logarithmic form or exponential form? Exponential form. So what am I eventually going to get to? Logarithmic form. Somehow, some way, possibly. Okay? So let's look at this first. Here's my exponent. So I need that to get isolated so that I can solve it. So what's going to be my first step on both sides? Divide by 40. So I have 1/2 raised to the x over 2 is equal to, what's 5/40ths reduced? 1/8. 1/8. Okay, if the base of the exponents are the same, then therefore the guys, stay with me, okay? If the base of the exponents are the same, then my exponents have to be what? The same. This goes back to the very first rule that we just talked about at the very beginning. If the base of the exponents are the same, then the exponents have to be the same. Why am I concerned about that? Because that is where my variable is lying. And if you notice that this base is 2, and I'm talking about the denominator, I'm kind of ignoring, since 1 is in the numerator, I can kind of ignore that for right now. If this base is 2 and this base is 8, can I rewrite 8 with a base of 2? Meaning, can 8 be rewritten as 2 raised to some power? Yeah, 2 to the what power? Third. 8 is the same thing as 2 cubed, correct? Correct. With that premise, I'm going to say 1/2 raised to the x over 2 is the same thing as 1/2 raised to what power? What'd you guys just say? 2 raised to what power? 3. Do I care about this one right here? No, no. I mean, I do care because it's 1/8, not 8, but 1 times 1 times 1 is just 1. It's nominal. Have I now created same bases? What can happen to those?
You can take those away.
I can. So I'm left with x over 2 is equal to 3. Therefore, x is
6.
x is 6. Could I have used my snail method going from exponential to logarithmic form?
Yeah.
I could have. If this do you guys want to see that? If this confuses you, do you want to see how to do that? Once you divide by 40, you're left with 1/2 raised to the x over 2 equals 1/8. Okay, so let's take it from here. Okay. Therefore, then, if my base, once a base, always a base, start with the base. Once a base, always a base, start with the base. So I'm going to have log. What's my base going to be? 1/2. So I'm snailing around. So log base 1/2 of 1/8 is equal to x over 2. And then on your calculator, you can literally type in log of 1/2 of 1/8, log 0.5 of 1/8 equals x over 2 and solve it from there. And this actually equals 3 equals x over 2, and therefore multiply both sides by 2, x equals 6. So that is a second way in which you could solve that using the snail method. Okay, just going backwards. Okay? You guys are super quiet today. You're either 100% lost or you're getting it like no big deal. I love that. Good answer. Okay, number 2. Like I said, we're kind of going backwards here. 2 to the 3x equals 3 to the 4th. Say what? First question that you ask yourself if you're in that, like, say what? Is this exponential? Is this logarithmic? It is exponential. Can I do anything with it the way it is? No. Meaning, can I take 2 to the 3x? No. Could I take 3 to the 4th? Well, I could do that. I'm not sure it's going to get me anywhere, but I could. So I can go in and I know that if I'm in exponential, I want to solve, I want to get it into logarithmic form. Okay? So instead of just throwing in a log, what can I do to both sides? Can I bring in my own logs? Yes, but what I do to one side, I have to do to the other. That's the premise of algebra. That's the premise of solving an equation. Okay, you got to keep everything balanced. What's this base here? And I'm looking at this because that's where my variable is. What's the base of this exponent right here? 2. Base is 2. Everybody see that? Everybody see that that's a base of 2?
Yes.
Okay. So therefore, what's my log have to be? Base of 2. What is 3 to the 4th? Before I go ahead and write that out, it's 81. So let's just go ahead and let's just simplify that. And what happens here? Those cancel. 3x equals, and then on your calculator, take log base 2 of 81. I think you get 6.34. And x equals, divide both sides by 3, x equals 2.11. You could also use snail. Knowing that this is 81, once a base, always a base. Log base 2 of 81 equals 3x, and solve it that way. Okay, so there's 2 different ways in which you could have solved that. Going from exponential to logarithmic You can throw in the logs, or you can use the snail and moving that around.